Assalamu alaikum. Good morning. Today we'll cover the second lecture in the respiratory system, which is the diffusion of the respiratory gases, which is the exchange of gases between alveoli and blood, and also between the blood and the peripheral tissues. The objectives of today's lecture are to discuss the dead space, minute ventilation and alveolar ventilation, and to explain the external and internal respiration, also to cover the differences in composition of atmospheric, alveolar, inspired and expired air, and state the partial pressures of gases in the inhaled and exhaled air, and to illustrate the changes in partial pressure of oxygen and carbon dioxide during external and internal respiration, and also to describe the factors that affect the rate of diffusion of oxygen and carbon dioxide. In the previous lecture we touched a little bit the dead space concept. We have something called the anatomical dead space. This consists of air that remains in the conducting airways or in the conducting zone of the respiratory system. This air does not contribute to gas exchange, as the wall of the conducting zone is thick and does not allow the movement of gases across it. As we said in the previous lecture, the volume of the anatomical dead space is about 1/3 the tidal volume, which is 150 milliliter. There is another dead space which is called the alveolar dead space. These are alveoli that contain air but do not undergo gas exchange. The volume of gas within non-perfused alveoli. These are alveoli that have no blood flow. The blood flow in the capillaries surrounding them is very low or zero, so they are not perfused, thus they do not participate in the gas exchange. Alveoli that are ventilated but not perfused with the venous blood. The total dead space, or also we call the physiological dead space, is the summation of the anatomical and alveolar dead space. So the value depends, usually the anatomical dead space value is fixed 150 ml, but the volume of the alveolar dead space is variable, and therefore the volume of the total or physiological dead space is also variable. The ratio of the total dead space to tidal volume is usually about 1/3. So the total dead space represents 1/3 of the tidal volume. Now let's see, in the previous lecture we come to know the Boyle's law, where the pressure of a gas is inversely related to its volume at a constant temperature. Dalton's law states that each gas in a mixture, like the atmospheric air, so each gas in a mixture of gases exerts its own pressure, as if no gases or no other gases were present in that mixture. The pressure of a specific gas in a mixture is called the partial pressure of that gas. The total pressure of the mixture is the summation of all the partial pressure of gases in that mixture, and we'll see a practical example about Dalton's law, which is the atmospheric air. For example, the atmospheric air pressure, which is 760 millimeter mercury at sea level, is equal to the total of nitrogen partial pressure, oxygen partial pressure, water vapor partial pressure, plus the partial pressure of carbon dioxide and the partial pressure of other trace gases. Each gas in the mixture diffuses across a permeable membrane from where its partial pressure is greater to the area where its partial pressure is less. So if we have a membrane separating two gases, the gas molecule from the area of high pressure will diffuse across the membrane to the area of low pressure, provided that this membrane is permeable to this gas. The greater the gradient, or the partial pressure gradient, or the greater the difference, the faster the rate of diffusion. Now let's go back to remember the two terms that we studied in the previous lecture. These are the alveolar ventilation and minute ventilation. As you remember, minute ventilation is the total amount of gas that flows into or out of the respiratory system in 1 minute, and it is equal, or it is the product of tidal volume and respiratory rate, and we said in the previous lecture it is about 6,000 milliliter per minute. So the minute ventilation at rest is 6 liter, and it increases during exercise up to 200 liters per minute to provide the required amount of oxygen for the skeletal muscles. Alveolar ventilation is the volume of gases that flow into or out of the lungs, it is the volume of gases that flows into or out of the alveoli in 1 minute, and it is the product of the gas in the alveoli, which can be obtained by subtracting dead space volume from the tidal volume and then multiply the resultant volume by the respiratory rate. So it is equal to 350 ml multiplied by 12 breaths per minute, and the final product is 4,200 milliliter per minute. Because dead space in an individual is normally constant, it doesn't change, so it is 150 and remains at that level. Alveolar ventilation is affected by tidal volume and respiratory rate. So if we want to change the alveolar ventilation, we have to change the tidal volume and the respiratory rate. But changing which one will be more effective in increasing the alveolar ventilation, we'll see in the coming lines. Significant increases in alveolar ventilation are brought about by increasing the tidal volume rather than increasing the respiratory rate. So if we want to increase the alveolar ventilation effectively, it is better to increase the tidal volume rather than increasing the respiratory rate. Rapid, shallow breathing can actually decrease the alveolar ventilation. It won't help in increasing the alveolar ventilation, and we can see the examples here in this table. As you see here, we have normal rate and depth of breathing or ventilation. The dead space volume is 150 ml, the tidal volume is 500 ml, and let's see here, or let's take this example where the respiratory rate is 20 breaths per minute, doing some mild exercise. The minute ventilation is 10,000 ml per minute, but if we calculate the alveolar ventilation by multiplying 350 by 20, it will be 7,000 ml per minute. So the percent effective ventilation is 70%. Let's see the second example where we have slow, deep breathing. Again, this change in the tidal volume and respiratory rate will not affect the dead space volume, but the tidal volume is high because we have deep breathing. The respiratory rate is low because we have slow breathing, so it is at 10 breaths per minute. The minute ventilation is 10,000 ml, similar to the previous example. If we calculate the alveolar ventilation by multiplying 850, 1000 minus 150, it is 850 by 10 then the alveolar ventilation is 8,500 milliliter per minute. So the percent effective ventilation is 85%. In the third example, we have rapid shallow breathing. Again, the dead space volume is 150 ml. Tidal volume is low because the breathing is shallow, 250 ml. The respiratory rate is 40 breaths per minute because we have rapid breathing. Now we have if we subtract the dead space volume from the tidal volume, we have 100 ml multiplied by 40, so we get an alveolar ventilation of 4,000 milliliter per minute, which is 40% effective ventilation. Again, you can see that the minute ventilation is 10,000, but the alveolar ventilation is different in the three examples, and the best alveolar ventilation is achieved when we have deep, slow breathing. So increasing the respiratory rate without increasing the tidal volume will not help in increasing the alveolar ventilation. Gas exchange occurs between lungs and blood, as well as between blood and tissues, the peripheral tissues. We have a term called external respiration or pulmonary respiration, which is the diffusion of gases between the blood and the lungs across the respiratory membrane. The internal respiration or tissue respiration is the diffusion of gases between blood and peripheral tissues. The exchange of oxygen and carbon dioxide in both processes, the external and internal respirations, occurs via passive diffusion, which is governed by the behavior of gases as described by the two gas laws, and the composition of the alveolar gases. So the chemical structure of oxygen and carbon dioxide, they are small molecules. They can directly diffuse through the phospholipid bilayer of the cells that form the barrier between the air in the alveoli and the blood, and between the blood and the cell in the peripheral tissue. Just to remember that according to Dalton's law, the partial pressures of gases in the inspired air, the partial pressure of nitrogen is 597.4 millimeter mercury. The partial pressure of oxygen, that represents about 20.9% of the atmospheric air, is 158.8 millimeter mercury, and for hydrogen is about 3 millimeter mercury, and for carbon dioxide 0.3, and other trace gas is 0.5. If we take the total of all these partial pressures according to the Dalton's law, we'll get the total pressure of the gas, which is the atmospheric air pressure at sea level, 760 millimeter mercury. So compared with inhaled air, exhaled air contains less oxygen because oxygen will diffuse down its gradient into the blood. So the percentage will drop from 20.9 to 15.9, and the exhaled air will contain more carbon dioxide. The percentage will be 3.6 versus the 0.04% in the atmospheric air or the inhaled air. Now there are differences in the composition of the atmospheric, inspired, alveolar and expired air. And this difference is due to several factors. Here we can see the percentage of the different gases in the atmospheric air, where nitrogen is the main gas, then oxygen about 20.9%, and then 0.04 for carbon dioxide, 0.5 for water vapor, and will give me a total of 760. Inspired air, when it is inhaled, it will pass through the conducting zone, and one of the main functions of the conducting zone is humidification of air. So water vapor will increase in that mixture, So we notice here that the percentage of water in the humidified air that passes, as it passes through the conducting zone, will increase from 0.5 to 6.2. This will cause dilution, small dilution in other gases. So we have the total finally at 760 millimeter mercury. As air enters the alveoli, it will reach the alveoli where oxygen will enter the blood and carbon dioxide will leave the blood into the air, or the air in the alveoli. As you notice, after diluting the nitrogen, there is very minimal change in nitrogen because nitrogen is not exchangeable. It doesn't cross the respiratory membrane. If you notice here that due to the movement of oxygen from the air in the alveoli into the blood, the percentage of oxygen will drop to 13.6 versus 19.7. And as carbon dioxide leaves the blood and enters the alveoli, the percentage of carbon dioxide in the alveolar air will increase to 5.3 compared to the 0.04% in the inhaled air. The percentage of water vapor will not change, and finally we have the total pressure of the gas in the alveoli at 760 millimeter mercury. Now the air will be exhaled during exhalation, and you will notice that the oxygen will be a little bit higher and the carbon dioxide will decrease compared to the alveolar air. Why? Because the air that leaves the alveoli will mix with the humidified air that remains in the dead space. So the percentage of oxygen will increase slightly, and that for carbon dioxide will decrease slightly, and the total will be again 760 millimeter mercury. Therefore, the exhaled air is different, or the composition of the exhaled air is different from the alveolar air, because as I said, when alveolar air is pushed outside the respiratory zone, it will pass through the conducting zone that contains humidified air. The mixing of that 350 ml with 150 ml of humidified air will change the composition of the alveolar air. Now let's talk about the second law in the respiratory system, which is the Henry's law. The Henry's law states that the quantity of a gas that will dissolve in a liquid is proportional to the partial pressure of the gas and its solubility. In the body fluids, the ability of gas to stay in a solution is greater when its partial pressure is higher and when it has high solubility in water. So the higher partial pressure of that gas at an air-fluid interface, this will make more gas to enter into the fluid. And if the gas solubility in that fluid is high, so we have more gas that will dissolve in that fluid or in water. When we compare oxygen and carbon dioxide is dissolved in the blood because carbon dioxide is 20 times more soluble than oxygen. Please don't forget this piece of information. The solubility of carbon dioxide in water or in plasma is 20 times higher than the solubility of oxygen. At sea level, very little amount of nitrogen dissolves in the blood plasma because of its low solubility. So nitrogen has very low solubility, so we won't find a high amount of nitrogen in the blood, although its partial pressure in the atmospheric air is high. So as I said, gas exchange occurs via partial pressure gradients. The higher the gradient, the higher gas exchange. The exchange of oxygen and carbon dioxide at the pulmonary and tissue capillaries occurs by simple diffusion. I said oxygen, carbon dioxide They are small molecules, so they can cross the phospholipid bilayer of the cell. Oxygen and carbon dioxide diffuse down their partial pressure gradients. Each gas diffuses independently from the area where its pressure or partial pressure is higher to the area where its partial pressure is lower. For example, the partial pressure of oxygen is greater in the alveoli. It is about 104 millimeter mercury compared to its partial pressure in the blood of the pulmonary capillaries, where the partial pressure is 40 millimeter mercury. So the partial pressure of oxygen in the alveoli is 104 and its partial pressure in the pulmonary capillaries is 40. So this gradient will favor the movement of oxygen from the air in the alveoli to the plasma of the blood in the pulmonary capillaries. By this gradient, oxygen diffuses from the alveoli into the pulmonary capillaries. On the other hand, the partial pressure of carbon dioxide is greater in the blood of the pulmonary capillaries. It is 45 millimeter mercury compared to its partial pressure in the alveoli, which is 40 millimeter mercury. By this gradient, carbon dioxide diffuses from the blood in the pulmonary capillaries into the air that is present in the Okay, in this figure we can see how it works. If you notice here that the partial pressure of oxygen in the alveoli is 105 or 104 millimeter mercury, while its partial pressure in the deoxygenated blood that flows into the pulmonary circulation to the pulmonary capillaries is 40. So the partial pressure in the alveoli is higher than that in the blood. Therefore, oxygen will move from area of high partial pressure to area of low pressure. So it will move from the air in the alveoli to the blood. The partial pressure in the deoxygenated blood that flows to the lung is 45 millimeter mercury, while its partial pressure in the alveolar air is 40 millimeter mercury. The partial pressure gradient is in favor of carbon dioxide movement from the blood into the alveoli. If we go to the tissue, here the opposite will happen. Now we have oxygen in the blood that has a partial pressure of 100 millimeter mercury. It will arrive to the tissue in the systemic capillaries that supply the tissues. The partial pressure of oxygen in the cells that continuously use oxygen is 40 millimeter mercury. So the gradient is in favor of oxygen movement from the blood into the cells. Cells that are actively performing metabolism, they produce carbon dioxide, so the partial pressure of carbon dioxide in the cells is 45 millimeter mercury, which is higher than its partial pressure in the oxygenated blood that supplies the tissue. Therefore, the carbon dioxide will move down the partial pressure gradient into the blood to be carried to the lungs to get rid of it. Okay, now let's talk in some detail about the external, or what happens in external or pulmonary respiration, and what happens in the internal or tissue respiration. Here we can see that we have different alveoli. The alveoli are supplied by pulmonary extensive network of pulmonary capillaries. The alveoli are lined by type 1 alveolar cells, and there are scattered type 2 alveolar cells that secrete the surfactant, which reduces the surface tension and improves the lung compliance that we discussed in the previous lecture. Oxygen in the alveoli or carbon dioxide in the blood, they have to cross something called the respiratory membrane. The respiratory membrane is composed of 3 layers. It is composed of alveolar epithelium, mainly type 1 alveolar epithelial cells, then diffused basement membrane of the epithelium of the alveoli, and the epithelium of the capillaries. The third layer is the capillary epithelium, and we call the endothelium. As I said, oxygen and carbon dioxide, they can cross the phospholipid bilayer at high speed. So if this respiratory membrane is thin enough, oxygen and carbon dioxide exchange will be very efficient. External respiration or pulmonary gas exchange involves the exchange of oxygen and carbon dioxide across the respiratory membranes. As you see here in this figure, oxygen will diffuse from the alveoli into the capillary to be carried by hemoglobin inside the red blood cells, and carbon dioxide will diffuse in the opposite direction to enter into the alveoli and then removed by exhalation. The respiratory membrane is a blood-air barrier that consists of alveolar and capillary walls along with their fused basement membranes. It is very thin. It has a thickness of 0.5 micrometer. This very thin respiratory membrane allows gas exchange across the membrane by simple diffusion. Capillary wall consists of endothelial cells. This is a simple squamous epithelium that lines the blood vessels, including the capillaries. Alveolar walls consists of single layer of squamous epithelial cells, type 1 alveolar cells that represent 95% of the alveolar wall, and scattered low cuboidal type 2 alveolar cells that secrete the surfactant, which reduces the surface tension, and also some antimicrobial proteins that help in the defense against pathogens or microbes, and type 2 cells represent 5% of the surface area of the alveolar wall. The partial pressure gradients and the solubilities of gases are responsible or help this gas exchange. The steep partial pressure gradient for oxygen exists between blood and the alveoli. Alveolar partial pressure of oxygen is 104 or 105 millimeter mercury. The partial pressure of oxygen in the venous blood that is carried to the lungs through the pulmonary trunk is 40 millimeter mercury. This steep partial pressure gradient will drive oxygen flow from the alveoli into the blood. The equilibrium is reached across the respiratory membrane in 0.25 seconds. The one red blood cell will pass from one end of the pulmonary capillary to the other end of the pulmonary in 0.75 seconds. So this is the time that is needed by one red blood cell to travel from one end of the pulmonary capillary to the other end of the pulmonary capillary. However, the red blood cell becomes fully oxygenated just after it crosses 1/3 of the capillary length, just in the first third of the pulmonary capillary, as we'll see in the next slide. This ensures adequate oxygenation. This efficient and very fast oxygenation will ensure adequate oxygenation even if the blood flow and the pulmonary circulation increases 3 times, because we have a spare 0.5 second for any additional blood flow. The partial pressure gradient for carbon dioxide is less steep. Venous blood, a partial pressure of carbon dioxide is 45 millimeter mercury, while the partial pressure of carbon dioxide in the alveolar air is 40 millimeter mercury. So the gradient is less compared to the oxygen gradient across the respiratory membrane. Though the gradient is not as steep compared to carbon dioxide, compared to oxygen, carbon dioxide still diffuses in equal amounts with oxygen. Why this? Because carbon dioxide is 20 times more soluble in the plasma and alveolar fluid compared to oxygen. So the less steep partial pressure gradient for carbon dioxide is compensated by the higher solubility of carbon dioxide in the plasma membrane as well as in the body fluid. As I said, one red blood cell takes about 0.75 seconds to pass from one end of the pulmonary capillary to the other end of the pulmonary capillary. However, the red blood cell will become fully oxygenated just after 0.25 or the first third of the pulmonary capillary, and the remaining 2/3 are spare if we need to increase the pulmonary blood flow 3 times. Again, we can still have full oxygenation of the blood as it passes through the pulmonary capillary. Okay, now let's talk about the pressures that affect the oxygen and carbon dioxide movement or exchange during external respiration that happens in the lung. Oxygen diffuses from alveolar air into the blood pulmonary capillaries due to the partial pressure difference. The diffusion will continue until the partial pressure of oxygen in the pulmonary capillary blood matches that of the alveolar air, so until we reach equilibrium. Small amount of mixing with blood from the conducting zone of the respiratory system will cause a drop in the partial pressure of oxygen in the pulmonary veins to 100 millimeter mercury. As I explained in one of the previous slides, that partial pressure of oxygen in the blood supplying the tissue is 100. It is about 5 millimeter mercury less than the blood leaving the lung, because the blood leaving the conducting zone will mix with the blood coming back from the alveoli. For carbon dioxide diffuses from the deoxygenated blood in the pulmonary capillaries, where the partial pressure is 45 millimeter mercury, into the alveolar air, where the partial pressure of carbon dioxide is 40 millimeter mercury. Diffusion will continue until blood partial pressure of carbon dioxide reaches 40 millimeter mercury, and this is the partial pressure of carbon dioxide that will be in the blood supplying the tissues. There is a concept called ventilation-perfusion coupling. Perfusion is the blood flow reaching the alveoli. So it is the blood flow into the pulmonary capillaries that supply the alveoli. Ventilation, as we studied in the previous lecture, is the amount of gas that reaches the alveoli. Ventilation, to have efficient gas exchange and without having low oxygen or excess carbon dioxide in our blood, we need to match the rates of ventilation and perfusion. So ventilation and perfusion rates must be matched for optimal and efficient gas exchange. Changing diameters of local arterioles and bronchioles will synchronize the ventilation perfusion. So the homeostatic mechanism will play with the diameter of the pulmonary arterioles and the bronchioles in order to match the rates of ventilation and perfusion and get a very efficient gas exchange. And this concept of ventilation perfusion matching will be further discussed in details in the respiratory module in phase 2, inshallah. Both ventilation and perfusion are controlled by local autoregulatory mechanisms. Partial pressure of oxygen controls perfusion by changing the arteriolar diameter, and the partial pressure of carbon dioxide in the alveoli controls ventilation by changing the bronchiolar diameter. And as I said, the The autoregulatory mechanism to match ventilation and perfusion will be discussed in more details, inshallah, in the respiratory module. What is the influence of local partial pressure of oxygen on perfusion? Changes in the partial pressure of oxygen in the alveoli causes changes in the diameter of the alveoli. High alveolar oxygen causes dilation or dilatation of the pulmonary arterioles. So alveoli that contain high oxygen will get more blood flow. So here we have better oxygenation of that blood because it passes or it supplies well ventilated alveoli that contain high alveolar oxygen. Low alveolar oxygen will cause constriction of pulmonary arterioles. So alveoli with poor ventilation that contain low oxygen, they will receive less blood flow, and the blood flow will be diverted to better ventilated alveoli. This directs blood to go to alveoli where oxygen is high, so blood can pick up more oxygen. So it will make the process of external respiration more efficient. Opposite mechanisms are seen in systemic arterioles that dilate when oxygen is low and constrict when oxygen is high. What is the influence of partial pressure of carbon dioxide on ventilation? Changes in partial pressure of carbon dioxide in alveoli cause changes in diameter of the bronchioles. High alveolar carbon dioxide will cause bronchodilation. So this will promote better ventilation of the alveoli, and this will remove this excess or high alveolar carbon dioxide. Opposite to that, low alveolar carbon dioxide means that the alveoli are well ventilated, so bronchoconstriction will happen. This will lower the alveolar ventilation. This allows the elimination of CO2 more rapidly. Here in this diagram you can see a summary of the ventilation-perfusion coupling as I explained in the previous slides. Now let's talk about the movement of oxygen and carbon dioxide, or the exchange of oxygen and carbon dioxide in internal or tissue respiration. Oxygen diffuses from the systemic capillary blood, where it has a partial pressure of 100 millimeter mercury, into the tissue cells. As I said, the partial pressure of oxygen in the cells is 40 millimeter mercury because cells constantly use oxygen to produce ATP through the aerobic metabolism process. Blood oxygen drops to 40 millimeter mercury by the time blood exits the systemic capillary. So as the blood exits the capillary, the partial pressure of oxygen will be 40 millimeter mercury. For carbon dioxide diffuses from tissue cells where its partial pressure is 45 millimeter mercury into the systemic capillaries where its partial pressure is 40. So the partial pressure here in the oxygenated blood is 40, while the partial pressure of carbon dioxide is 45. So carbon dioxide will move from area of high partial pressure to area of low partial pressure, and this will continue until equilibrium will happen, and the partial pressure of carbon dioxide in the blood leaving the tissue will be 45 millimeter mercury. Cells constantly make carbon dioxide. Diffusion will continue until blood carbon dioxide partial pressure reaches 45 millimeter. The rate of pulmonary and systemic gas exchange depends on several factors. Number one, the partial pressure difference of gas, or the partial pressure differences of gases. Alveolar oxygen partial pressure must be higher than that of blood for diffusion to occur. So if we go to high altitude, the partial pressure of oxygen in the in the atmospheric air will be low. This will lead to lower partial pressure of oxygen in the alveoli, and this will lead to less gradient, so the driving force for oxygen to move from the alveoli to the blood will be less. So this will affect the diffusion of oxygen. The other factor that affects the rate of pulmonary and systemic gas exchange is the surface area available for gas exchange. The surface area may increase during exercise as more capillaries open because of the increased cardiac output, and alveoli are expanded more as breathing becomes deeper. So with exercise, we increase the surface area of the respiratory membrane, and this will increase the pulmonary gas exchange. The diffusion distance is the other factor that affects the pulmonary as well as the systemic gas exchange. And in the pulmonary gas exchange, the diffusion distance is the thickness of the respiratory membrane. So the diffusion distance is the distance separating air and blood across the respiratory membrane that normally has a thickness of 0.5 micrometer. The last factor is the molecular weight and the solubility of gas. As oxygen has lower molecular weight, it could be expected to diffuse faster than carbon dioxide, but carbon dioxide has higher solubility than oxygen, 20 times higher solubility. So the net outward carbon dioxide diffusion occurs 20 times more rapidly than net inward oxygen diffusion. In emphysema, which is a condition where there is destruction of the alveolar wall, this will reduce the surface area. So the surface area will become less, and this will lead to less gas exchange. In another condition, like in heart failure, pulmonary edema will cause thickening of the respiratory membrane, so the distance, diffusion distance will become longer, and again this will decrease or inversely affect the diffusion or the exchange of gases. Let's talk about some clinical correlations related to the gas exchange or diffusion of gases. There's something called effective thickness of the respiratory membrane. The effective thickness of the respiratory membrane increases dramatically if the lungs become edematous, as in pulmonary edema. That is seen in heart failure or in pneumonia, infection of the lungs. So the 0.75 seconds that red blood cells spend in transit through the pulmonary capillaries might not be enough for the adequate gas exchange. This time could not be enough for full oxygenation of the blood as it passes through the pulmonary capillaries. This results in a condition where body tissues will suffer from oxygen deprivation. Certain pulmonary diseases drastically reduce alveolar surface area, and this will lead to reduction of the respiratory membrane. Example is emphysema, where walls of adjacent alveoli break down and the alveolar chambers will enlarge. Again, tumors, mucus or inflammatory material also can reduce the surface area by blocking gas flow into the alveoli. They will block the ventilation of the alveoli, so this will increase or decrease the surface area that is available for the gas exchange. Thank you very much for your audience. Any questions, please don't hesitate to contact me by email. Thank you.